the wave functions for hydrogen. So we will move on to the solutions of the Schrödinger equation, where the simplest solution is the 1s solution. So n equals 1, L equals 0 solution, S sub shell. So this is K shell, S sub shell. 1 over square root pi Bohr radius A0 cube exponential decay e to the minus r over A0. Now if you investigate what this solution is doing, as r goes to infinity, you see that the solution decays to 0 as we required, and this is a spherically symmetric solution. So it has the same value depending on the radial distance r, whichever direction we go away from the nucleus. Now, the probability of finding an electron in a volume dV would be given by the square of the wave function, psi squared, this is the probability density function, multiplied by the volume of the region, dV. So psi squared dV is the probability of finding the electron in a volume dV. So this would be, if I go to the probability of finding it in a radial distance r to r plus dr, it's the probability density function of r, which is a function of r times dr. So how do I obtain this? Well, I note that dv in spherical coordinates is basically 4 pi r square. So if I'm at a radial distance r from the center, that is the surface area of the sphere multiplied by its thickness dr. So it's 4 pi r squared dr. So if I'm at a radial distance r here, if I move another distance dr, 4 pi r squared would be the area of this surface multiplied by dr gives me the volume of the shell. Shell thickness dr, right? So psi square multiplied with 4 pi r squared dr. So probability density function as a function of the radial distance r is not absolute value of psi square, but absolute value of psi square multiplied with 4 pi r square, where 4 pi r square is the surface area of the sphere with radius r. So this is the radial probability density function. So we can obtain the radial probability density function for the simplest solution, 1s solution. So it would be 1 over square root pi a0 cube. We have to take its square, so it would be 1 over pi a0 cube. And then we have 4 pi r squared, the square of this one e to the minus 2r over a0. So we will obtain, because we have a pi, square root pi squared here, pi's will cancel, and we will be left with 4r squared on top, and a0 cube, a square of the square root gives us the a0 cube, e to the minus 2r over a0. This is the radial probability density function. Okay, so if you plot this probability density function, radial probability density function, as a function of r, we find that this actually increases at the beginning with the square of the radius, and then it decays exponentially, so this part will dominate for higher radii. This shows us a maximum, and the maximum corresponds to the Bohr radius, 0.0529 nanometers. That gives us the most probable distance, radial distance, from the nucleus. And this agrees well with the Bohr theory. Now, if you look at this representation, if you plot this in 3 dimensions, this is x-axis, y-axis, and z-axis is coming out this way. That's the z-axis. We see that first we have r equals to 0, 0 probability, and then we have the probability increasing, making a maximum at r equals a0, and then it decays exponentially. If we plot this in the full space defined by xyz coordinates, we get this what looks like a cloud. So we call this the electron cloud. So the electron charge may be thought of as being extended throughout a region of space, which is called the electron cloud. So this is going to represent for us the 1s orbital radial probability distribution. Basically, it shows us the probability of finding the electron in the space that is defined by x, y, and z coordinates here, and the most probable position is a single Bohr radius r is equal to a0. Now the next simplest wave function is n equals to L equals 0. That's L shell with the S subshell. So psi of 2S radial solution, which is 1 over 4 square root 2 pi, 1 over a0 to the power 3 over 2, 2 minus r over a0, e to the minus r over 2a0. And if you plot this one, we obtain the radial probability distribution function as 4 pi r square psi 2s absolute square. This gives us two peaks, and the most probable position we find to be at 5a0 instead of a0 in the 1s solution. Okay, so we've talked about some solutions of the Schrödinger equation. Basically, these are the ones that have the radial part. That's the 1s solution and 2s solution, and they basically both show an exponential decay as r goes to infinity, so that the probability of finding the electron far away from the nucleus goes to 0. And the 1s solution is spherically symmetric, and in order to move from the probability of finding the electron in a volume dv between v to v plus dv, we have to go to radial probability density function dr. That is the probability of finding the electron in a region between r and r plus dr. That is absolute psi square 4 pi r squared dr, because this is replacing dv. 4 pi r squared dr is the volume of the shell, which has thickness dr and a radial distance r from the center. So 4 pi r squared absolute value of psi square is the radial probability density function. If we calculate this for the 1s solution, we find the most probable solution as at a single Bohr radius. And if we plot this solution in three-dimensional space, we obtain what we call the electron cloud. So electron charge may be thought of as being distributed throughout a region of space called the electron cloud, where the most probable position is at r equals a0. And a similar solution for n equals to L equals to 0, 2s orbitals gives us this result. And this one has two peaks instead of one, and the most probable solution turns out to be at 5 Bohr radii.